Hello everyone, welcome to part 3 of Equivariant singular instanton homology. As you probably already know by now, this is based on a joint work with Chris Scaduto. In the last talk, in part 2 of this series of talks, Chris explained how to associate to a knot in S3 and S complex. In fact, he talked about two different S complexes. One is the one which is given by Z coefficients, the other one was an S complex which is defined in terms of some local coefficient system. An important property of this invariant for us is its functoriality with respect to cobordisms. In order to explain the framework, the right framework for functoriality, I have to give some definition for the morphisms of S complexes. So let's fix two S complexes given by the triples C tilde, D tilde chi, and C tilde prime, D tilde prime, and chi prime. So a homomorphism of the abelian group C tilde and C tilde prime, which is graded, so remember that both of these two guys are graded and we require that this map has degree 0 with respect to these gradings. We say any such homomorphism is an S-morphism if it satisfies these conditions. So firstly, it's a chain map, which means that it commutes with the action of the differentials D tilde prime and D tilde prime. D tilde and D tilde prime. Secondly, it's supposed to be commuting with the action of chi and chi prime. And finally, if you look at the map induced by the action of lambda 2 from the kernel of this operator chi over the image of chi to the kernel of chi prime quotient by the image of chi prime, then this map is supposed to be identity. To get a better feeling about this, let's fix a splitting of our S complexes C tilde and C tilde prime. This means that C tilde has this standard form and C tilde prime has a corresponding standard form. So then we can write down lambda 2 with respect to this splitting of C tilde and C tilde prime. And then we would get this block form for lambda 2. So the main constraints here are that we have these three blocks being 0. These two diagonal blocks are supposed to be equal to each other, and finally this last block, which is supposed to be from Z to Z, is supposed to be the identity map. After sorting out the definition of S-morphisms in the algebraic picture, now we can talk about the functoriality of singular instanton floor homology. So fix two knots K and K prime in a concordance from K to K prime. This means that we have a properly and smoothly embedded surface S inside an interval times S3, where the boundary of S is equal to the union of K and K prime. To be a little bit more precise, we should think about going from left to right in this picture as going, moving inside the interval. So this is where we are at time 0, t equals 0. So our knot K is at the intersection of our surface S and 0 times S3, and this is where we are at time 1, the intersection of 1 times S3 times 1 times S3 and our surface S. The package of singular instanton floor homology to any such concordance associates an S-morphism from the S complex of K to the S complex of K prime. Whenever you have a concordance from a knot K to K prime, you would get for free another concordance from the knot K prime to K. All you need to do is to just flip this cobordism S to get this concordance. So I'm going to call this other concordance by S bar, which would give us an S-morphism from the S complex of K prime to the S complex of K. So in summary, whenever we have a concordance, we can get S-morphisms in both directions, from the S complex of K to the S complex of K prime, and from the S complex of K prime to the S complex of K. This motivates the definition. We say two S complexes C tilde, D tilde chi, and C tilde prime, D tilde prime, and chi prime are local equivalent if there are S-morphisms in both directions between them. So there we have an S-morphism lambda tilde from C tilde to C tilde prime, and similarly we have an S-morphism lambda tilde prime from C tilde prime to C tilde. This discussion here tells us that if you have a concordance between two knots K and K prime, then the associated S complexes are local equivalent. The notation that we use for local equivalence is this. So we write C tilde is equivalent to C tilde prime. It is also straightforward to see that this notion is an equivalence relation. And I should say that the definition of local equivalence is partly inspired by similar concepts in other versions of Floer homology. So up to this point, we only talk about functoriality with respect to concordances. This version of functoriality can be extended to more arbitrary cobordisms, and some of these sort of cobordisms would show up later in the talk. So this more general version of functoriality will be important for us. It is natural to ask whether this notion of local equivalence is non-trivial. Are there any general abstractions for local equivalence? It turns out the answer to this question is yes. There are some Froyshov type invariants which would give us such abstractions. I like to define Froyshov type invariant an integer associated to an S complex where we fix a splitting like this for our S complex, and the differential with respect to the splitting is given as here. We divide the definition of this invariant, which is called h of C tilde, into two cases. The first case is when this map delta 1, which is a homomorphism of C star to Z, is non-trivial on the space of cycles on the kernel of D. In this case, h of C star tilde is going to be defined as the maximum of all integers I, such that there is a cycle alpha satisfying this property, that if we compose V j times and then compose it with delta 1, it acts trivially on alpha if j is less than I minus 1, and it's non-trivial if j is equal to I minus 1. So from the definition, it's almost clear that this is always a positive integer. So in this first case, we would get a positive integer. The second case is when delta 1 acts trivially on the space of all cycles. And again, we would define this as maximum of integers I, such that we can find a cycle, but this time we also need a bunch of integers a0 up to a minus I, such that the differential of alpha can be written as delta 2 of a0 plus delta 2v of a1, all the way up to delta 2v to the negative I, a minus I. So as it is clear from our notation here, I has to be some negative integer. So in particular in this, or it could be also 0. So in this second case, h of C star tilde would be some integer which is not positive. And there's a proposition here which says that if we have two local equivalent S complexes, then they have the same value of h. So if I would encourage you to pause the video and go back and try to prove this proposition. Is very straightforward. And I should say that this proposition and the definition of this Froyshov type invariant appears in a slightly different form, but essentially the same construction in one of Froshov's construction when he defined an integer homology cobordism invariant for 3 manifolds. Now that we learned something new about the algebra of S complexes and S morphisms, we can go back to our topological setup and see if it gives us something new. So for any knot k, we define an integer associated to k, which is supposed to be h of the S complex associated to the knot k. So this h is what we defined a few seconds ago for any S complex, and then h of k is supposed to be this algebraic guy. So it's always an integer. From the definition and the property behavior of equivariant singular instanton homology with respect to concordances, it should be clear that h is a concordance invariant. we can even get some more properties of this invariant. So firstly, we can see that H is additive with respect to connected sums of knots. This is in fact a consequence of the connected sum formula that Chris talked about at the end of the part 2 of this series of talks. In fact, we can say also something more about more than just being a concordance invariant. For any knot k, absolute value of h of k gives us a lower bound for the non-orientable genus of k. So this gamma 4 of k is the non-orientable genus of k. Furthermore, we have some computations for this invariant. For example, for any alternating knot k, h is 0. In fact, the same is true for any quasi-alternating knot. And for any torus knot TPQ, this h of TPQs can be computed as the sum of two other invariants. So the first one is the signature of our knot, which is the classical invariant. The second one is upsilon of our knot TPQ, which is an invariant defined by Froyshov, Lipschitz, and Zabel. In particular, they define this invariant to get some lower bound for the non-orientable genus. So this identity also is closely related to property 2 of H. So in summary, we would get some non-orientable genus bound out of this invariant, and this non-orientable genus agrees with after adding signature of our knot divided by 2, it agrees with Froyshov, Lipschitz, and Zabel's upsilon invariant. It would be interesting to see if these two invariants, to find some knots that these two invariants are not equal to each other. Alternatively, we can replace C tilde of our knot K with this other version of S complex associated to knot K, which is defined using the local coefficient system delta. And this way we obtain a new Froyshov type invariant, which we call it HS of K. Remember that this local coefficient system was defined in part 2. And the interesting feature of this invariant is that it can be completely computed. It's not a new invariant. It's equal to the signature up to a constant, which is -1/2. At the beginning, it might seem kind of disappointing that you didn't get a new knot invariant, but in fact, we will see that this identity has some topological implications. Next, we turn to our definition of the invariant gamma. The definition of the invariant gamma requires some additional structure and S complexes associated to knots. So here we're going to work with the S complex associated to the knot using the local coefficient system. Remember that it means that it's a module over this Laurent polynomial ring in 2 variables. So we have this which splits into 3 segments. So the first one is again another module over this ring. Then we'll have another sum, which is the shifted version of that guy, and then finally we have a rank 1 segment. The main property here is that each graded version here, Ci of k and delta, it meets another grading. So remember that I here is an integer which is related to Floor's grading, but then there is this j, which is a real valued grading. It takes values in a set A, which is the set of Chern-Simons invariants of K. So this is a discrete subset of real numbers, potentially including some irrational numbers, and it's invariant with respect to shifting by integers. So we call this second grading I grading. So both this guy, they have this I grading, And then finally, we also regard this rank 1 summand as some I-graded module where when we look at the term u to the j times t to some power, then the I grading is equal to j. So once we set up this r times z by grading on our S complex, we can see that our differential detail doesn't increase the I grading. So the differential is filtered with respect to the I grading. Furthermore, if we have a cobordism, a concordance from a node k to another node k prime, then if we look at the associated S morphisms, this one doesn't increase the I grading. So this motivates an enriched version of the notion of local equivalence. We say two enriched S complexes, which mean S complexes with these additional structures, with this additional I grading, so that the differential doesn't increase the I grading. Our local equivalent, if there are morphisms in both directions, lambda tilde and lambda tilde prime, satisfying this property. So firstly, these morphisms are supposed to be S morphisms. And secondly, they are filtered with respect to I gradings on C tilde and C tilde prime. So this I grading gives us, these two I gradings and C tilde and C tilde prime would give us some filtration, and we want our morphisms to be filtered with respect to filtrations. I should make a remark here that the description that I gave here is not quite accurate. In general, our Chern-Simons functional might be degenerate in an appropriate sense, in which case we have to add perturbations to our story and define the Chern-Simons filtration by some limiting process. In any case, we would get some notion of enriched complex, and it turns out that enriched complexes up to local equivalence would give us a much richer structure than regular S complexes up to local equivalence. So, for example, there are much more abstractions, and the invariant gamma is one such abstraction. So next I'm going to give the definition of gamma, which is supposed to be, this can be defined for a general enriched complex, but here I'm just going to define it for a knot. So it's a function defined on integers. Like the definition of h, we have to divide it into two different cases. When I is positive, it's going to be defined in terms of the I grading of some elements of the complex C star of alpha. Remember that it has a bi grading. We require this integer grading to be 2i minus 1 when this I is the same as this I. And then we'll look at the I grading of this element. So this alpha is not an arbitrary element. It's supposed to satisfy some conditions that you would find it very familiar as the one, because it looks very similar to the condition that we use in the definition of the invariant H. So alpha has to be cycle, and this condition about delta 1 composed with powers of v applied to alpha should be satisfied. Similarly, you would get some definition for the case that I is less than or equal to 0, so you have to repeat a very similar definition, except that the expression that you have here is now is the one that you would use for the definition of Froyshov invariant H in the case that the Froyshov type invariant H in the case that we're looking in the case that invariant is negative or 0. But in this case, there's a subtlety which I don't want to get into it. But this is not gonna be good, and we have to take the maximum of this number and 0. So if this infimum is some negative number, then you should take the maximum with 0, in which case you would get 0. It is probably a good time to look at an example. Let's consider the case of the trefoil. In this case, the S complex C tilde with local coefficient system is going to be decomposed into, and it has this standard splitting. So the part which we have to figure out what it is as a module is C star of the trefoil. It turns out that it's a rank 1 module over our underlying ring, a ring of polynomial, lowering polynomials in two variables u and t. And this guy, of course, has a z times r by grading. And when we look at the element u to the k, t to the l times the generator here, that element has this by grading. So the integer grading is 4k plus 1, and the real grading is k plus 1/3. For grading reason, you can see that most of the terms in the differential, they have to be 0. So like the differential on C star has to be 0. The map V has to be 0. Delta 2 also has to be 0. And the only possible non-zero term is delta 1, which is supposed to be a map from C star to our underlying ring. And we can explicitly compute that by looking at delta 1 as zeta, we would see t squared minus t to the negative 2. And finally, if we look at, given this characterization of our complex, we can easily compute the gamma invariant for the trefoil, and we would get this value, which was also mentioned in the first talk. I'd like to look at some properties of the invariant gamma k. The first property is that gamma k takes values in the set of Chern-Simons invariants A or infinity. If you look at the definition of gamma k, you would see this property almost immediately, because the possible values for I grading is this set A, and in the definition of gamma k, it could be it's possible that we're taking infimum on an empty set, so in which case we would get infinity. In fact, we can completely characterize when we would get infinity. Gamma k at some integer is finite if and only if this integer is less than or equal to negative signature over 2. So you probably can identify this term with the singular Froyshov invariant that we talked about before in the case of local coefficient systems. And in fact, that's the starting point. So this property is coming from the similarity in the definition of gamma k and the singular Froyshov invariant. This function gamma k is a non-decreasing function. And finally, we get to the most important property for us, which is behavior of gamma k with respect to more arbitrary cobordisms than concordances. Let's say that we have an inverse cobordism from some knot k0 to another knot k1. So it has a number. So it has genus, which we denote by G, and it has S plus and S minus positive and negative double points. Based on this topological invariance, we define this number L, which is important for us because it's a call to index of some elliptic operator, which plays an important role in the construction. And now, if this number is non-negative, then we have that gamma k1 at I plus L is less than or equal to S plus over 2, the number of double points divided by 2, plus the value of gamma k0 at I. So it would allow us to get some upper bounds for gamma k1 in terms of gamma k0. 2 remarks about this inequality, or maybe 3 remarks. So the first thing is that this number L, this condition that L is non-negative, seems to be a technical condition. We think that it's probably not necessary, and one might remove this condition by some work on the technical part of the story. The next comment is that please note that asymmetrical role, which is played by the genus G and the number of double points, you would see that this condition is not symmetrical with respect to these variables, and that's how we can get some lower bounds for 4-dimensional class number, which wouldn't work for the slice genus. Finally, I should say that this inequality is also a consequence of functoriality of S complexes with respect to more arbitrary cobordisms. In fact, with respect to cobordisms of which form, of this form where L is greater than or equal to 0. Now we want to apply this inequality to the special case that the incoming n is the unknot and the genus is equal to 0. So then the quantity L is equal to negative signature over 2, and remember that the invariant gamma of the unknot is given as follows. So now if you look at the inequality that I gave in the previous slide, in the case that I is equal to 0, you would get this inequality. And since this is true for any inverse cobordism from the unknot to R naught K, we can conclude that this guy gives us a lower bound for 1/2 of the 4-dimensional class number. This was the key inequality for us in the first talk. I'd like to end my talk by mentioning a variation of gamma k. In the definition of gamma k, you can replace the S complex with local coefficient system with the S complex with Z coefficients, in which case we would get another invariant, which we call it gamma kz. This is a refinement of the singular Froyshov invariant with Z coefficient. Remember that this was a non-orientable genus bound. So this way we would get some invariant gamma kz, which is related to the non-orientable genus, and potentially could have some more additional information. All right, so that's all I have for today. Thank you for your attention.